Hello everyone. In today's lecture, let us discuss about synchronous up-down counter. In the previous class, we have discussed about synchronous up counters. Today, we are going to discuss about a counter which can count upward as well as downward. A counter is a device which can count any particular event on the basis of how many times a particular event is occurred. Normally, counters are implemented using flip-flops. And these are the different applications where counters, up-down counters are used. Timers, digital clocks, frequency dividers, and in microprocessor for program counter incrementing and decrementing, up-down counters are being used. Now we are going to learn how to design an up-down counter. So here listed is a design procedure for designing an up-down counter. So step 1 is to select the required number of flip-flops and the type of flip-flops of our choice. Step 2 is draw the excitation table for the flip-flop. Step 3 is draw the state diagram. Step 4 is draw the excitation table for the logic diagram. And fifth step is to draw the K-map and to find the minimal Boolean expression. And sixth step is to draw the logic diagram for the up-down counter. Now we are going to discuss a problem statement. We are going to design a synchronous 3-bit up-down counter. The first step, as we have said earlier, we have to select the number of flip-flops and the type of flip-flop. To perform 3-bit up-down counting, 3 flip-flops are required, which can count up to 2 power 3 minus 1, that is up to 7. Here we are going to use T flip-flops. In the case of synchronous up counters, we have used JK flip-flop. So all the counters can be designed using any flip-flop. Once after selection of the flip-flop and the number of flip-flops, the next step is to draw the excitation for the particular flip-flop. Here we have chosen T flip-flop and this is the excitation table for the T flip-flop. Excitation table is where present state and the next state was given and the input is calculated. And now this is the state diagram to show the synchronous up-down counter. So as we know, it is a 3-bit up-down counter, so it can count up to 0 to 7. And here, since it is doing both the up counting as well as down counting, we need an extra input which we call it as the control input. Here, M is mentioned as the control input. When M is equal to 0, then the counter will perform up counting. When M is equal to 1, the counter will perform down counting. So see, this is state 1. From state 1, it is when M is equal to 0, it performs up counting. That is, it has to move to state 1. When M is equal to 0, it has to move to state 2 and so on. When M is equal to 1, it has to move to the lowest. That is, from 1, it moves to 0. From 7, it moves to 6. And this is the path where the loop closes. From 6, it moves to 5 when M is equal to 1. So when M is equal to 1, it performs as a down counter. And when M is equal to 0, it performs as an up counter. That is why this M is known as the control input. So this is how we represent a state diagram for an up-down counter. And here we have the excitation table for the up-down counter. So as we have discussed earlier, we have two types of inputs, control inputs. Either M could be 0 or it could be 1. And here we have, it's a 3-bit counter, and since it is a 3-bit counter, we have 3 flip-flops. And so we have the three outputs of the three flip-flops too. That is Q1, Q2 and Q3, as well as the complements of that, the next states of that, right? So this is the present states and these are the next state. So when we consider a 0, 0, 0 with a control input 0, then it means it is an up counter, and so the next state will be 1. When the present state is 0, 0, 1 and when m is equal to 0, it is again an up counter, and so the next state will be, we have here as 0, 0, 1, and so this will be 0, 1, 0, that is 2. Similarly, it will go till 7. And now if you see here, for example, let me take this 7, 7, 1, 1, 1, right? So if the present state is so, then it moves to the previous state. Consider this example 0, 0, 1. If you see the state diagram 0, 0, 1, where is 0, 0, 1? Here we have 0, 0, 1. When m is equal to 1, the next state is 0, 0, 0. For 0, 0, 0, when m is equal to 1, the next state is 1, 1, 1. That is what is mentioned here. When the present state is 0, 0, 0, the next state is 1, 1, 1. When it is 0, 0, 1, the next state is 0, 0, 0. And this is how we'll be filling the present state and the next state. So once when we know the present state and the next state, we can write the value of t from the excitation table. So here we'll be comparing x3 with x3 star. That is, this is the present state for the third flip-flop and this is the next state for the third flip-flop. When q is equal to 0 and q star is equal to 0, then t will be equal to 0. This is what we write from. When present state is 0, next state is 0, t will be equal to 0. From this excitation table, we have to write, we have to fill this excitation table for the logic diagram. So now our aim is to find the inputs for all the three flip-flops. That is, we have to find the value of T1, T2 and T3. For this, we need to draw K-map to find the Boolean expressions. Draw a K-map to find the minimal Boolean expressions. So this is the K-map to find the minimal Boolean expressions. So for T1, T2 and T3 we have drawn the K-map and we have derived at some Boolean expressions. And this is the logical diagram. So see here we have given the control inputs, right? Along with the control inputs, we T1. If T1, it is logic 1. If you see T2, it is OR operation of m q1 dash and m dash q1. So we'll derive m dash from this q1 as well as m q1 dash. And the output of these two is added to with this and is given to T2. And this bubble here, it represents that this is a system with negative edge triggering clock, nothing else. So this is how we have to design. So this system, and it has been implemented, will help you to count the numbers from 0 to 7 as well as from 7 to 0 back. So that is what it is known as an up-down counter. And here you have certain questions for your assessment. How many flops are required to design a 4-bit counter? How many states will be there for a 3-bit counter? And thank you.